Hi everybody, this is Mr. Yeoman, and today we're talking about limiting reactants. In the past, we've talked about how a chemical equation is kind of like a recipe, and so below I have the Nestle Toll House chocolate chip cookie recipe, and in it looks just like any other basic recipe, showing that you need 2 1/4 cups flour, a teaspoon baking soda, sugar, brown sugar, and then we go down here 2 large eggs. Now, when you're cooking, sometimes you find out, well, all right, I don't have 2 large eggs. You open up the refrigerator and only have 1 egg. Well, does that mean no cookies? Not at all. So, as a lot of you are probably already thinking, is that you can just cut your recipe in half. So, I can still use 1 large egg, but I'm only going to use 1 cup of chocolate morsels, a half a teaspoon of baking soda, so I can still have everything in the same proportions. I just need it to be in half of what the recipe originally calls for. And so the same thing is true in chemistry, is that just because we have a certain amount of substance, that may mean that if you had already gotten out a teaspoon of salt, you're not going to use all of it. So I'm going to provide a couple of examples right now. So at the top here, I have a chemical equation. This is hydrogen and oxygen forming water. Now, off to the side, you see a rocket, and these are the common propellants that we use for rockets, is liquid hydrogen and liquid oxygen. When they come together, then they produce this exothermic reaction. The byproduct is water, but that provides a lot of the lift for these rockets. And so what I have here is I wanted a visual that would show you what was happening at an atomic, at a molecular level. So I have hydrogen, okay, so 2 hydrogen atoms, and I have oxygen, so 2 oxygen atoms, and I just randomly chose 4 of each. And so when those combine, what's going to happen is I am going to get 4 water molecules. And you can see here that I have 2, 4, 6, 8 hydrogen atoms, and over here on my product side, I also have 2, 4, 6, 8 hydrogen atoms. However, we run into a little bit of a problem in that there's 8 oxygen atoms on our reactant side, and we're only using 4 of them at this point. So what ends up happening is we have 4 extra oxygen atoms, so 2 oxygen molecules that are left over. So in this case, that would tell us that the hydrogen is our limiting reactant because we have an excess of oxygen. Okay, so in this situation, our hydrogen is our limiting reactant because it limits how much water we can actually produce. Okay, so another example. Looking at this picture, this is a picture of a stovetop burning a hydrocarbon, in this case methane. And I have the formula for methane below there, so it is CH4, that's methane, plus 2 oxygen molecules forms carbon dioxide and water. So our mole ratios here is 1 to 2 to 1 to 2. So for every 1 mole of methane, or every 1 molecule of methane, we're going to need 2 moles or 2 molecules of oxygen to produce 1 molecule of CO2, or 1 mole of CO2, and 2 molecules or moles of water. Okay, so if we take a look at this next slide, we have our reactants in our product. So we have our CH4 and our oxygen. So we have 1 CH4, 1 methane molecule, and I have just 4 oxygen molecules here. So you might already be able to look at this and tell me what the limiting reactants are, or reagents are. But looking at that equation again, we should be producing, for every 1 molecule of CH4, we should be producing 1 molecule of carbon dioxide and 2 molecules of H2O. And that is exactly what we have happen, is that we have 2 moles of water, 2 molecules of water, and 1 molecule of carbon dioxide. But again, just like we saw in the last situation, on our reactant side, we had 4 molecules of oxygen for a total of 8 atoms of oxygen, and we're only using 4 atoms of oxygen over here. So that means that we have 2 atoms of oxygen left over. So that would indicate to us that we have an excess of oxygen, meaning that methane was our limiting reagent, our limiting reactant. Okay? So using what we've learned, then we can use some of this information in order to figure out what our results will be. So let's say that I just started with 10 grams of methane and 10 grams of oxygen. I could use all the steps that we've determined through our stoichiometry unit in order to figure out how much product we would necessarily need. So all I have to do is pick a product and I can convert to that. So just like we were using on that map, that diagram that I'd given you, we could take that 10 grams of CH4 and that 10 grams of oxygen, and we can convert those out of grams and into moles. Okay, so what I have here is the formula weight, or the molar mass of methane. And so I know that 1 mole of methane weighs 16.05 grams of CH4, which we get from the periodic table. Same thing is true down here for oxygen, is I have 32 grams for every 1 mole, so I took the formula weight, the molar mass of oxygen, so each oxygen has a mass of approximately 16.00 grams, and there's 2 of them, so that comes to 32. Okay, so that's great, and we now have this in moles, but we also need to compare how are these moles being used. So in this situation, we have different mole ratios. For every 1 mole of methane that we are putting into this equation, we're going to get out 1 mole of CO2. However, it requires 2 moles of oxygen for every 1 mole of carbon dioxide. Okay, so that's going to change our result a little bit because we need twice as much oxygen as we need CH4. So that could end up changing our results a little bit. Okay, our last step is to convert to grams. So we're going to do the same thing that we did over here, except instead of moles being on top and grams being on bottom, we're going to do the opposite. And because we were converting to CO2 on both of them, this step looks exactly the same for both of our equations. The molar mass or formula weight of carbon dioxide is 44.01 grams for every 1 mole of CO2. Okay, so now we have everything that we need. We have calculated these to a common possible product. And so now all we have to do is multiply across. So I'll take 10 divided by 16.05 times 1 divided by 1 times 1 divided by 1 times 44.01. There are a number of different ways that you could calculate this, but they all come out the same way. I do the same thing down here at the bottom, and my result is that for the 10 grams of CH4, if all of that methane reacted, I could get 27.4 grams of CO2. Okay? However, for the oxygen, if I have 10 grams of oxygen, then I can only get 6.88 grams of CO2 if all of that oxygen reacted. Okay, so that's a big if, but even if all of that reacted, we'd only get 6.88 grams of CO2. So in this situation, before I was using a visual, and the oxygen was our limiting reactant because I just put a bunch of extra oxygen into the equation. But in this situation, because we usually measure out these chemicals by mass, then we can calculate this out and determine that oxygen is our limiting reactant, because if we start with 10 grams of oxygen and 10 grams of methane and we just put them together, then we're only going to get 6.88 grams of CO2. And we'd have a bunch of methane still left over. So that means that methane would be our excess, because if we reacted all the methane, we'd get a much larger amount of carbon dioxide. Okay, so this comes in handy as a chemist. So if you're going to think about this as an actual chemist would, this would be important because you'd always want your limiting reactant to be whatever is more expensive, because you don't want to have any of that wasted. In this case, if I added extra methane, if oxygen was something that I couldn't get a hold of very easily, which we know that isn't true. But if one of these was something that we couldn't get a hold of very easily, then I would want to calculate how much I actually need. And I could actually do that in this situation as well. If I know that 10 grams of oxygen is my limiting reactant, then I could take that 6.88 grams of CO2 and I could put that into the equation and work this backwards and say, all right, if I want to get 6.88 grams of CO2, how many grams of methane would I need in order to calculate that out, in order to react that? Okay, so this is just kind of how that works. We're just using stoichiometry, but we're taking it a step further in how we are using that. All right, so one more example here. This is probably going to look a little bit more similar to what you are typically going to be doing. So you might be given a situation where I want you to figure out how much iron 2 sulfide will be produced if I start you off with 9.68 grams of iron reacting with 6.28 grams of sulfur. Okay, so this is just a synthesis reaction, but the first thing that we need is an equation. Okay, and more than that, we need a balanced equation, but in this case, it is balanced. It is 1 to 1 to 1 mole ratio. So I can start off with 9.68 grams of iron, and as we talked about before, you can also write this as over 1, because in math, that's how it works, is you can always add those items in. And I need to use that formula mass. Okay, so or I'm sorry, in this case it is just the molar mass of iron. So 55.85, I get that directly from the periodic table. That is under 1 mole of iron. Okay, I now use my mole ratio, so 1 mole over 1 mole. So I can convert out of moles of iron into moles of iron 2 sulfide. And that leads me to trying to convert into grams of iron 2 sulfide. Okay, so that is 87.91 grams of iron 2 sulfide for every 1 mole of iron 2 sulfide, which gives me 15.2. Okay, so if I go across and I take 9.68 divided by 55.85 times 1 divided by 1 times 1 divided by 1, and obviously you don't have to do all of that. Just want to make sure that you know these numbers don't just disappear, but mathematically they don't do anything for us. So we take that and multiply it by 87.91 and we get 15.2. And as we've always done, you can double check to make sure that you have the right label, because we wanted to make sure that we were getting grams of iron 2 sulfide, so we can cancel out any labels that are available to us. So we have grams of iron and grams of iron, so those are going to cancel out. Moles of iron, those cancel out. Moles of iron 2 sulfide, those are going to cancel out. And so we're left with grams of iron 2 sulfide. So that's what goes in as our label. Okay, so we can repeat this with our other reactant, which is 6.28 grams of sulfur. And just like before, we can put 1 under there if you prefer to make it a fraction. But then we need the molar mass of sulfur. So 32.06, again, directly from the periodic table. Use our mole ratio, so it's a 1 to 1 mole ratio. And then this last step, just like in the previous one, this is not going to change because we're still converting into grams of iron 2 sulfide. We need something common to compare them to. So now I just solve it, get 17.2, cancel out my labels, and that means that my label is grams of iron 2 sulfide. So that's great. I've done these equations, but now it comes to the important part to figure out whether or not this is going to, which one is our limiting reactant. So if I react all 9.68 grams of iron, I will only get 15.2 grams of iron 2 sulfide. If I react all 6.28 grams of sulfur, then I will get 17.2 grams of iron 2 sulfide. So this shows me that the iron is my limiting reactant, because I can only get, if I react all of that, I will only get 15.2 grams. Whereas if I react all of the sulfur, then I will get 17.2. Be careful. A lot of times people look at this when they're first starting to try to do limiting reactants. They look at this and they say, oh, well, these numbers are different. This one is smaller, so obviously that's the limiting reactant. That's not always true. Remember, iron is a very heavy element. So it will take more of it to make 1 mole. 1 mole will weigh more. So that's what you're trying to take a look at. Even though this is a 1 to 1 ratio, you need to go through and be able to solve these problems, because otherwise it's not going to come out quite right. So looking at the end, again, whichever number is smaller, that is going to be our limiting reactant, because it's saying that's the maximum amount we can produce. All right. thanks for your time today, and I will get another video here to practice some more of these so we can do them together. Have a great day, and I will see you soon.